In this segment, we'll examine the assembly for set bit from the primes.c program that's right up here in the diagram. In this and the following segments, we'll move to a guided tour mode, asking you to think through the code on your own as much as you can. To this end, there will be many in-lecture questions asking you to analyze and comment segments of the assembly listing for primes.s. Please get a copy of this, preferably a numbered one, and comment it as you view and read the lecture. The assembly for setBit is at the bottom of primes.s, and it's excerpted here. The first 5 instructions set up a stack frame, so let's look at those. And we'll start with question 1. What is not being saved in this stack frame that was saved in all earlier examples? And extra credit if you can guess why it isn't being saved this time. A hint, by the way, note that setBit doesn't call any other functions. Well, the answer here is that setBit doesn't save the LR register. We don't need to because setBit makes no other function calls, no BLs in here, no BL calls, to overwrite LR, so LR won't change during the setBit call. So setBit just stores the old FP and then moves FP to point to the bottom of the new frame. Question 2 real quickly. Can you rewrite line 162, add FP SP0 more simply? I think we'd probably agree as an answer here that this could have been just a move instead of a add. In earlier stack frame examples, this instruction would have been something like add FP SP4, but the lack of LR storage makes it add FP SP0 here, and that really should be a move instruction. Compilers are sometimes just dumb. Question 3. How many words are reserved for local variables and for parameters to be stored? Where are the parameters prime and prime set stored relative to the top of stack? And are all the local words used? And the answer on that question is that it's reserving 3 words since 12 bytes are subtracted from SP. And the top 2 words are for prime at 1 word below the TOS and for prime set right at the TOS. FP at the bottom of the stack frame, the -8 reaches just 1 word below top of stack, and the -12 reaches to the top of stack. Not all 3 words are used, as there is no reference anywhere to FP-4 in the setBit code. Again, sometimes compilers are just dumb, and this may be a side effect of the fact that it never bothered to save LR, but didn't adjust the stack frame accordingly, the stack frame size accordingly. And then question 4, comment those first 5 lines based on the discussion we've had. And a reasonable answer will be given for you to compare with. And here's a block of comments that might have been appropriate, or anything like it would be fine. We're pushing old FP onto the stack, starting a frame, or pointing FP to the base of the new stack frame, or reserving 3 words, write prime into the middle word, write prime set into the top word. Okay, so let's go on to look at the next 5 lines. These 5 lines right here compute the location of the desired prime set element. So we're not computing the value of that element, but its location. They introduced shift operations in ARMAssembly. Before examining them, think about the relationship between prime set, which is a pointer, contains the address of the first integer in the array, and the address of the desired element. What is the difference between those two? For instance, I've got a picture of prime set here. If prime is 87, then the desired bit will be somewhere here in index 2. And that index 2 element is 8 bytes in from the start of the array. So, question 5. How many bytes, in general, are between the start of the array and the start of the desired element at index prime minus bits parent? Do this concretely for cases where prime is 31, 32, 127, 128, 1020, 4088. Part of the point there is to get you to compute a general rule rather than doing it ad hoc. Do the computation for each of those values then until you come up with a consistent rule. Divide by this, multiply by that sort of thing, to compute the byte offset, again, for the right array element within prime set. If your rule includes a division, what should be done with any remainder? Drop it, round to the nearest int, and don't forget that each element of the array occupies 4 bytes. Okay, so some concrete answers to what might have been a bit of thought. The element holding bit 31 is at 0 bytes offset, because it's in the first element, it's in index 0. But bit 32, right over the border there, is in index 1, so it's at 4 bytes offset. Not just 1 byte, 4, right? Each element takes 4. Prime 127 is way out here in element 3, index 3, so 12 byte offset. But 128 actually is just over the border in index 4, so that's 16 bytes for it. And the general rule is that we get an index by dividing the bit number by 32, dropping the remainder, and then multiply that by 4 to get a byte offset. That puts 1020, for instance, at 1020 divided by 32 times 4, 124 bytes. And 4088 divided by 32 times 4 is 508 bytes. This sort of computation is what a compiler does anytime you use an array element. It figures out the index, multiplies by the size of the array elements to get a byte offset from the start of the array. Okay, now let's look at those next 5 lines of code. The second and third lines, these two here, in that group, introduce something new. Many ARM instructions, including move, add, and sub, though not loader and stir, will let you add a shift specification to the last operand. This takes the form of a 3-letter shift type and a shift amount. The LSR5, for instance, specifies a logical shift to the right, logical shift right, LSR, by 5 bits. Recall the difference, by the way, between logical and arithmetic right shift. A logical shift won't sign extend. ASL2 specifies an arithmetic shift to the left, in this case by 2 bits, though arithmetic versus logical, by the way, is sort of irrelevant in left shifting. So an LSL2 would have done the same thing. The shift amount can be a constant, as it is here in these 2 instructions, or it can come from a register. For instance, if R1 contains 4, then LSR R1 would shift right by 4 bits. Shift specifications will not shift by more than 31 bits. The CPU circuitry that performs shifts is designed only for this maximum shift amount, and trying to shift, for instance, by 32 bits results either in an assembler error if you tried it with a constant, or in surprise behavior if you use a register. In the latter case, you'll generally get a shift by 0 instead of by 32. This issue arises sometimes when coding shift operations in C. Shifting by 32 or more is a bit useless anyway, since the result will always be either 0 or possibly -1 in the case of arithmetic right shifting. Question 6. Think about those 2 bit shifts and what we learned about the mathematics of bit shifting in earlier lectures. Based on that, explain what the first 3 lines of this block of code do. What value ultimately is loaded into R3 on line 168? And what value is loaded into R3 on line 166, and what value will be in R3 after line 168? My answer is that 166 loads prime into R3. That's where it was stored on the stack. The second line, 167, divides by 32, dropping any fraction, and third multiplies by 4. They compute the byte offset of the prime set element containing the desired bit, and that's what's left in R3. And note, by the way, that just left shifting by 3 wouldn't accomplish the same thing, since we wouldn't get the truncation of the fraction when dividing by 32. And so we arrive at question 7. What do the final 2 instructions, the LDR and the add here, accomplish? And then finally, after they're done, what's the value in R3? The answer here is that they load prime set, fp minus 12, which is the address of the start of the array, and then they add it to the byte offset in R3. So R3 now has the direct address of prime set indexed by prime divided by bits per int. Not just an offset, the direct address. And the next 3 lines, if you look at them, do exactly the same thing, but for R2 instead of R3. So R2 and R3 will both contain the address of the relevant array element. And that sort of redundancy will be corrected when we look at the optimized version of this code in a later module. So question 7 now. Please comment lines 166 through 170. And by default, you'll be doing that for 171 through 175. No need to repeat yourself. Based on the discussion we've had. And a reasonable answer will be given for you to compare with. So this would have been a reasonable set. Load prime into R3, divide prime by 32, rounding down to get an index. Multiply by 4 to get the byte offset of that index. Load the starting address of prime set, and add to the offset to get the address of the desired index. So let's move on a little here. Line 176, next one to consider, is deceptively simple. Just LDR_R2 bracket R2. Think carefully about it and describe what it does given R2's current contents. Add a comment describing that. The answer is that it uses R2 as an address and gets the word at that address and then puts it into R2. This might have been clearer if a different register were the target, but compilers like to reuse registers. A reasonable comment would be something like LDR_R2 bracket R2 load index contents into R2. The next 5 instructions deal with setting the correct bit in the word that we just loaded. In other words, they compute this C expression here, which we discussed in the prior segment. So the instruction AND R1, R2, pound 31 deserves a bit of explanation. This performs a bitwise AND operation on the contents of R1 and the constant value 31, putting the result back into R1. Recall prior discussion on what bitwise AND does. Here's an example of the instruction at work, assuming the contents of R1 is currently 42. The bit pattern for 31 has 1s in the bottom 5 bits. So those are the only bits that could be 1 after the bitwise AND operation is done. In effect, the operation keeps whatever the bottom 5 bits of R1 were and zeroes out all the rest. So what is the mathematical significance of that? There are 2 good ways to look at it. First, the eliminated bits are all divisible by 32. 32, 64, 128, etc. And the preserved bits are all non-divisible by 32. So this operation preserves the non-divisible by 32 part of R1's value, or in other words, it computes R1 modulo 32. The second way to look at it is that shifting R1 right by 5 bits divides by 32, as we've already discussed, and the 5 bits being preserved by the bitwise AND are exactly the remainder that is lost by that right shift. So again, R1 and 31 is the same as R1% 32. In general, we can accomplish a modulo by 2 to the x power via a bitwise AND with 2 to the x minus 1. And bitwise AND is much faster than performing a division. The compiler knows this and uses bitwise AND when possible. So sometimes compilers are smart after all. Okay, so question 10. Now that we understand what the AND instruction does, decipher the other 4 instructions and comment all 5 of them. And a reasonable answer, making a little room for them here, would be the following. The first instruction loads prime into R3. The second sets R1 equal to prime modulo 32. Third one puts a 1 in R0. And the fourth one shifts that 1 to the left by prime modulo 32 to get our 1. And then the final one completes the expression by taking the value of prime set prime divided by bits per int from earlier computation and ORing it with the shifted 1. You should be able to guess and can look up the fact that ORR is sort of the complement to AND. It does a bitwise OR operation. Okay, now R2 has the desired bit pattern with an extra 1 bit ORed in. Let's scroll this up a little bit. Question 11. Comment this line here, line 182, recalling what's in R3 from earlier instructions. The answer is that this is saving the bit pattern back into its original location, which is still, that address of the index is still in R3. And then finally, wrapping it up, we're left with just a couple of remaining lines here, 183 through 185, those 3 lines, I'm sorry. And question 12, you should be able to correctly comment these from earlier examples, so please do that. And a reasonable answer there would be that this first one, for instance, reasonable comments here would be that the first one, 183, removes the local space and sets SP back to the FP location. And then the LDR loads the old FP and moves SP back to the old top of stack. And then finally the BXLR returns to the caller via LR, which is unchanged. So this concludes the commenting work for setBit. In the next segment, we'll do checknum.